Good. All right, Mr. Ryan Dawson, big round of applause, please.
Okay, so sorry about the graphics quality. That's just because of the technical hitch we've had. They would normally look better, but I'll just run with it, and hopefully we'll be okay. So we are going to talk about ML ops or AI ops. There's variations on it at the moment, but one way or another, it's a buzzword. So this is kind of like, well, it is DevOps for machine learning. It's the DevOps specifically for machine learning. One might naturally ask the question, well, why is that not just DevOps? Why do we need a separate word? Why is there a whole fuss about this separate thing that's being called ML ops? And actually, if anyone's come across some of this ML ops stuff, like from a DevOps perspective, it can look a bit strange. So we're going to walk through the field and understand where this stuff is coming from and why we have a separate field of ML ops emerging. I can't see that, but yeah. Okay, so in order to do that, we need to take a bit of a step back and understand how machine learning differs from programming. So what's the difference? And in particular, we need to understand what the difference in terms of the workflow, like how data scientists work and what they do, and then how that drives MLOps concerns, why that gives rise to specific problems that are unique to MLOps. So then we'll dive into some of those particular topics, which are listed here. They don't need to make sense yet. And we'll also talk about some general challenges in the field. So I guess I don't need to explain about DevOps here, because everyone here knows and loves DevOps. But what is worth highlighting is that there's a certain kind of commonality around DevOps. There's a set of tools that people are familiar with that characterize the practices. So this is mostly like tools around CI/CD and infrastructure. And there's practices, and the organizations know how to engage with it. It's seen as a key way of getting time to value and governance out of software projects. MLOps is not in the same position right now. There are studies that suggest that about like in the region of 80 to 90% of ML projects just never go live. This diagram here is from quite a fairly famous paper by some Google guys about machine learning infrastructure and how people underestimate it. The little box in the middle, the really black one, that says ML code. So that's the actual model code. And this is trying to illustrate that actually, so like all the stuff around data processing and cleaning and extraction, there's got this huge space here on the left. And then there's all the stuff on the right. This is about running this thing in production. So why is that happening? That's what we want to understand. So why have we got these differences? Well, if we take a step back for a minute, what's the key difference? What are the key differences between these practices that are being serviced? Well, traditional programming is all about codifying behavior with explicit rules. You get some inputs, you want to respond to the inputs with outputs, and you're going to explicitly code that behavior, the translation. With machine learning, you don't codify things like that. Instead, the rules are set indirectly. That you capture patterns from data and you reapply those patterns. And there's typically different problem and domains accordingly. So machine learning is more applicable to kind of focused numerical problems. So it's a different kind of problem that one applies it to. So to make this a bit clearer, we can think about like traditional programming problems or space. This can be anything from like the old terminal systems where you like key stuff in, right through to like the complex games that we get now. And the way you progress with this is like you start with a Hello World app, like if you're learning programming, and you add more control structures. And this is like a learn to program thing where you write loops or code and it makes the turtle move. This is really quite different from machine learning problems. So machine learning problems typically fall under like regression or classification problems. So it's either you've got like a bunch of data and you want to predict a number out, Or a classification problem is like trying to put things, you get data inputs and you try and put it into a bucket. And the way that people get started with this stuff, like, so MNIST is a famous data set where you have like handwritten samples where people have written numbers down, and you need to try and figure out which number it is. Yeah, and then there's like the whole range of problems on Kaggle. Yeah, so some more examples might help to like make this even more clear. That you get regression problems like how to predict salary from a bunch of features like experience, education, etc. Or maybe you're going to predict the amount of sales a company can make based on like the spend that they do on advertising, or the type of advertising, and placement, and so on. And then there's classification problems. So I mentioned the handwriting samples one, or there's like image classification ones. Like lots of people love playing with cat pictures. Yeah, so just to characterize a bit more about how data science is different. So like the tools are different as well. So like a famous or the favorite environment for data scientists is Jupyter Notebooks. And these are designed to be interactive. Unfortunately, the GIF isn't working, but what you would see here is like we click into the notebook and you see interactive code cells, and you can click on a particular cell and it runs that cell, and you can click on particular cells and it will render graphs. So you can run Python code that will render graphs, and it renders it in the notebook, and you can share the notebook with other people and then collaborate around these notebooks. So they're great tools for exploration and visualization. So if you've got a data set, you can apply operations on the data set. You can like render pie charts and histograms and things, and just see the characteristics of the data set to explore it and figure out what the patterns might be that you can then look to extract through machine learning. And you may well also build the machine learning models in the notebooks. So it's going a bit further into the way that machine learning works. If the animation were here, you would be able to see this line kind of moving around, but you can't, so you have to imagine the line moving around. So essentially here we've got a bunch of data points, and we're trying to draw a fit line through the data points, because that fit line will then allow us to make predictions. So then when we get the coordinates in, we can then say, oh yeah, or like when we get one value in, we can say what the other value is. We can make a prediction. And the way this is done is by like setting a bunch of weights these W values up here. These coefficients represent weights, and that captures the equation. And then we infer values for those weights by like essentially setting random values and then adjusting them until we've got something that fits well. So we want to minimize the distance between all the data points and the line. So the distance between any data point and the line, that's part of the error or loss for the function. I mean, I guess everyone kind of is a little bit familiar with this, but I just want to remind everyone, because it's really important to see how this flows into all the concerns that come out of MLOps. Yeah, so I mean, this is just illustrating about the weights. You know, the weights aren't adjusted randomly. It's this process called gradient descent, where you figure out what adjustment is going in the right direction, and you carry on. We don't have to understand that in detail, though. The data scientists have to understand that in detail. We just need a sort of general picture here to understand what MLOps is about. So yeah, key points on machine learning. It's the training, in the training or fitting process, it's the data and the code together that are driving this. So it's not just your code. The data is crucial. That's how you extract patterns from data. The closest thing you get out of it to an executable is a model. So that's that set of weights together with the kind of the type of model that you're using. That is an embodiment of the model. You might have to do retraining because you've taken a sample of the data. So the data you use to do the fitting process, that was a sample. Like it's unusual to have the entire data set and be able to work with it. So when you've trained off this sample, so the patterns that you reapply are going to reflect the nature of the sample. So if the new data coming in differs from that sample in significant ways, then your model's not necessarily going to perform very well. So a good example of this is like in the fashion industry, where like the fashion moves in trends and seasons. So if you like train your models are based on one particular season, then when the new season comes along, it's not going to perform very well. It's going to start recommending like summer clothes when actually people are now buying coats. Yeah, so I should also highlight just this is very data intensive. The whole process, there's lots of data, and that means a lot of resources and things take a while to run. So let's go back to traditional programming now and think about the DevOps practices that are kind of characteristic of it. So in a traditional programming workflow, you've got a user story, you write some code, you submit a PR, the tests are going to run. Then when that gets merged, there's an executable built, probably gets packaged as a Docker container, and it's going to go through a promotion flow, and then you monitor it in production, like you look for any stack traces or error codes. This should be, I'm guessing it's pretty familiar. I hope I'm not saying anything controversial here. So the things get different when you think about machine learning, because the driver for that process that we just talked about is code change. But the driver for with machine learning might not be a code change. It might be that there's new data available. And that's probably not going to be in Git. I mean, Git's not a great store for data. When you're talking about data that goes into the gigabytes, it's just not really viable. The workflow is also different because machine learning workflows is just much more experimental and data-driven. So you've taken the sample, you need to play with it, and then you get a new sample, and you need to play with that. Also, the thing that you're looking for, like so when the tests, if you think about the way tests run in traditional like programming setups, like you know what behavior you're looking for, and it's a pass or it's a fail. But with machine learning, typically you're looking for quantifiable performance. So this is the types of indicators you're looking for are numerical. And there's a range of different cases, but let's talk about the case where you train a model offline and then you run it. Well, I don't want to talk about the case where the model's constantly getting retrained on every prediction. That's a kind of more complicated type of case. Yeah, so if we think about that kind of case for now, the case where we're doing the training offline, then we can characterize a broad kind of ML workflow. So we get some data. There's going to be pre-processing on that data, but let's just pretend that somebody else has done that, like some data engineers or something. So then, we've got this slice of data that's been processed, and you try stuff out. Once you get something working on your laptop, perhaps in a notebook, something that's got kind of good predictions, you're happy with the way that they're coming out, then you might want to take a larger sample of data, because locally you can only use a smaller sample compared to what you can run on a hosted environment where you've got access to more resources. You might want to collaborate with other data scientists, so ideally there's going to be some sort of hosted environment. Probably that's Jupyter notebooks, and that might be Git involved in that. The model may get pickled, so I guess I should probably say serialized. That might be a more familiar term. I mean, basically that's what Python pickling is a kind of object serialization, and that's a pretty common way to distribute machine learning models. Okay, so once you've got something that's distributable, you want to run it in an application. Like machine learning is of interest normally because it fits into some sort of wider business situation, which probably means a web app. It might not be a web app. It might be offline batch predictions or something.
Mobile devices.
Yep, yeah, mobile devices indeed. IoT, all that stuff. But yeah, okay, so so you might want to run a web app. That's called serving, actually. It has its own name within the machine learning space. You don't just call it running a web app. And then you might want to test it against the rest of the web app and monitor the thing for how well it's doing. And for some reason, I've got a pop-up on my screen. And I don't know where the mouse is. And we will fix this. Where?
You click on the slide and go left or right, which works.
Yeah, I just can't find the mouse pointer.
It's up there.
Ah.
It's behind.
Yeah. Thank you. Audience participation. That is my next slide, isn't it? Yep. Okay. Yes. Okay. So yeah, maybe it helped to think of a kind of an end-to-end type metrics-based example. So let's say you've got some sort of online store, and you want to roll out like a new version of a model. So perhaps the model is like telling you which adverts to show people or which products to recommend. And you've got you come up with a new version of the model that you think is going to do better. Based on the slice of data that you took, well, then you want to put it, when you put it into action, you can do an A/B test. So you split the traffic that the live system is servicing, and you say the existing model that's A, and then you take some of that traffic and you say that's going to be B, and that goes to the new model. And let's say that the new model actually does better in a certain respect. So maybe it does the thing that it was meant to do. So perhaps you get more conversions or more sales or something. But I mean, if you're showing adverts to people, I mean, actually, there might be like really aggressive pop-up adverts or something, and that might lead to more conversions, but might also really annoy some people. So there's all these kind of side effects that you can get. So you might get like bad reviews, or you might get more people leaving your site, even though the people that stay are more likely to buy. So that you can get these it's considerations that are embedded in the business context. Yeah, so just so what some people have been talking about in the ML space and how this whole ML ops is becoming such a buzzword at the moment is this concern that what's happening is the data scientists do stuff on their local machines, and then it gets shipped over to the team that's meant to actually run the thing in production, and they're like, well, what is this? Because if you get a Python pickle and no other context around it, then that's a pretty reasonable reaction. In a more kind of more mature setup, you might have something more like this, where you've got like specifically data engineers that do the pre-processing stuff and taking care of the wider data setup, and then data scientists that do the model building, and then you've got other people that are kind of machine learning aware that are doing the whole running thing in production and making it work with the rest of the app stuff. So I guess the way that MLOps comes into this is really about like providing ways to break down these silos and provide ways to collaborate, and also for the data scientists to do some element of self-service. So there needs to be like tools that are kind of oriented to the way that data scientists work, and that provide this new kind of space for people to collaborate more and solve these problems together. But it's a new space. There are special, as I say, some of these challenges are special. But we can understand it a bit better by dividing it up and taking some of these different areas and drilling into them now. I'm going to, in particular, we'll talk about training, how you take a slice of data and train a weighted model on it, and the tools that are available for that. And then we'll talk a bit about serving, so how you then take the step from trained model to running it in a web app. And then also the whole rollout and monitoring process, and the challenges that are specific to machine learning there. Okay, training and experimentation. So yeah, there's a bunch of platforms around for this. I mentioned some on here, kubeflow pipelines, polyaxon, mlflow. One of the key bits of it is like being able to run separate steps and break them down so that you can do things like all the cleaning and transformation on data. This is especially relevant in like natural language processing. So you might have steps like this where you like now need to download a whole load of data, and then you split it up into different like types of data that you're going to use in different ways, and then you run through the training and gather metrics on it. So that's just an example of what a kind of training pipeline might look like. Yeah, so this hasn't rendered very well, but this is just a screenshot from the Kubeflow dashboard. So the Kubeflow platform is specifically aimed at being an encompassing ML platform for Kubernetes. Pipelines is the one up here. There's also like Jupyter Notebook servers. There's an artifact store, that's what that says there. So this is more like about metadata tracking and knowing where all the models and the data and stuff is. This all kind of links up. And then there's like contributors that's about like managing access control, essentially, collaboration. Yeah, so we're going to drill into pipelines in particular. You probably, again, can't see this very well, but within pipelines, you have this idea of an experiment. And an experiment is essentially a training run, but the tool is geared towards having lots of parameters. So you can say, for this training run, plug in these parameters. So you might take a particular slice of the data set, or you might put in a bunch of different numerical parameters that guide the training process. And this is really in order to try out different values to see which one gives the best kind of predictions. And then you can monitor the training run on the right. So this is like showing the different steps in the run, how far it's got. You get the logs for them. Because you might set a bunch of these things off. Really? Okay. You might set a bunch of these running, and they carry on running for like days or whatever. I'm going to have to get a move on because we're running quite behind. Yeah, so mlflow has a very similar idea of experiments and parameters. Another tool tries to be an all-encompassing platform. These training platforms, they look kind of like CI tools, so like the whole training process is kind of like CI. But the fact that you're doing experiments is quite different from CI. So you need to be able to put these different parameters in and see what comes out. So some of them do have CI integration, but you need to like manage the fact that somehow somebody's got to make a decision about what counts as good in this context, which can be done, and it's just that it tends to be unique to the context. Okay, so let's say we've got a model. Now we're going to jump to the serving step. So we're going to assume that we want to serve it as an HTTP application. There's a bunch of tools that are available to do this. So a pretty common pattern is to take the package model and host it in a storage bucket, and then the serving solution can then run it. We can compare. So this is just like a Kubernetes hello world. I was going to compare that against what you would do in machine learning. So, but it's quite different. So, like the one that we just looked at, that you have a Docker image. Docker image is down the bottom there in the hello world. In the machine learning case, it's more common to have like a URI to a storage bucket. So this is the storage bucket. It's got a packaged model. You put the URI to the storage bucket and say what type of toolkit was used to package the model, and then it's able to serve predictions. So that's just because the serving solution knows about these types of toolkits, and then it's able to turn that into something that when you make a HTTP request to the predict endpoint, it can serve a prediction provided you've like sent in the right features or whatever it is, and there's like an API around that. Oops. Oh yeah. So serving is also linked to the whole rollout monitoring stuff. So we talked a little bit about A/B tests. Essentially, those are about traffic splitting. Canaries are another case of A/B tests of traffic splitting, but where you tend to do it for a shorter space of time. Basically, traffic splitting use cases are really important for machine learning because you want to be able to evaluate how well things are doing against, given that you took that sample and you trained off for a sample. Now you want to see how well is it going to do against the live data because it's different data, right? One way of doing this actually is another way is to do shadowing. So you just take all of the traffic and run it against two versions. So in order to facilitate allowing data scientists to do this, rather than having to get the ops people involved in all of the deciding about what rollout strategies, it's pretty common to allow for a canary, or one way is to allow for the canary to be defined in the manifest of the serving specification. So this is an example here from Selden, and we've got two models, and one's the canary and one's the main model. And there's another case here with traffic splitting with A/B testing. Okay, so let's say you've got these two models running, then you need to be able to figure out which one's doing better. So you need to be able to monitor these things now. And in the case of, so Selden, for example, provides out-of-the-box metrics to be able to see, to get a measure of how well the models are doing. So you get at least out-of-the-box metrics on things like how many requests are going through and so on. Because this stuff is commonly needed, and also it avoids the data scientists have to do work to get this stuff together. They don't want to. The data scientists don't want to have to do a lot of work to hook it up to Grafana. Instead, the serving solution just has out-of-the-box integration to Grafana. And likewise, there's out-of-the-box integration to the Elastic Stack for request logging. Again, this is something that's quite common in machine learning use cases. You might well be interested in finding out exactly what the prediction was made for a particular case. You might get it might be that you've got an application where you've got a very important customer rings up, wants to know, why did this your ML model say that this picture of Mr. Fluffy was a dog? It's a cat. Why, how did you make this mistake? It's terrible. So then you want to be able to go back and find that particular data item, figure out what the features were that fed into it, and be able to, if necessary, analyze it and understand whether it was a justified prediction in that case, and whether you need to retrain the model or make adjustments. I'd love to be able to show you the Selden UI, but we are pushed for time. But basically, that brings all these features together in a nice way and provides wizards to help enable the creation of the deployments. Okay, I'm just going to jump through the advanced topics. So there's more stuff that one might want to do. So you might also want, if you let's say you've got like feature pre-processing that happens on the data on the training data. It's plausible then that you might also need to do the same pre-processing steps on the live data, because if that's the raw form of the data, then you might have to do the same thing. So you might want to break out the steps and form a kind of pipeline, and there's other more advanced cases that you can handle then when you've got this kind of splitting of pipelines. Okay, so then there's a whole world of governance questions. Not just with like Mr. Fluffy, but like following on from Mr. Fluffy, there's like things about how do you explain why an algorithm's made the predictions in the case that it has. Certain techniques, actually that's really challenging. Neural nets in particular, it's very difficult to get into the details of why it did what it did. And then there's the issue of, well, like figuring out, okay, for a running model, the model that's running now, which training run produced that model? What was the training data that was used? Who triggered that training run? When did it happen? Linking all that up is quite challenging because there's quite a lot of different metadata around there, particularly about like being able to take link the metadata to the data version there. There's competing tools for metadata, so it's a rather complex space. I think that's probably about all I can say right now, actually. But I think that's, that's me. And that's MLOps.
Any questions?
Yep, we have a question in the front row.
Nice t-shirt, by the way. How much
Thank you.
more processing or time is required on an already working model set by adding new data into it? Is it faster to do retraining on a new data set, or is it extendable on the previous data set and model?
So there are cases where you can build on the existing. So if you've got you've got something pre-trained, you want to add more data, you can shorten the learning time with something called transfer learning, but it's a particular technique. Sometimes you just have to go back and train again from the very beginning.
So it's not common?
No, I wouldn't say it's the most common. No.
Thank you.
Any other questions? All right, thank you very much.
Cool. Thank you. That's not mine. Cool.